On example 1, we saw that the polynomial with infinitely many terms perfectly became e to the x for all values of x. And we knew what the function was that it was representing. We don't always have that luxury. Sometimes we'll have a power series that represents some function, and we won't really know what the function that the series is representing is. We don't know what the equation of it. But that won't keep us from analyzing the series itself, okay? So on example 2, we have this power series. And how do we know that that's a power series? Because of the x. The x, good, very good. And the series is a function of n, but when you expand it out, it becomes a function of x. What else can we say about this? Does anyone know where the center is? Can you spot the center just by looking at the rule of sequence? It's 5, right? If you remember from the Taylor's form, the x minus the center to the nth power is the variable part, and that's this right here. Okay, so you can always spot the center by looking at the x plus or minus. If it were x plus 5, the center would be at -5, right? And of course, if it were just x to the n, it would be a Maclaurin series. What else can you tell me about this power series besides the centers at 5? It's an alternating series. Good, because you have the alternator there. So your coefficients of the series are generated by that, and then the variable parts are the x minus 5 to the n. We want to know then, for what values of x does this series represent some function exactly, not approximated, that's polynomials, infinite series. We want to know for what values of x. Well, we know for sure that this series will be the same value as the function it represents, for sure at least at one x value to start, which is what? 5, right? Because the center is at 5. Every series and the function it represents have the exact same value at the center. But there could be more values, and that's what we want to figure out. Okay, so the radius of convergence helps us find the domain of the power series. And what test do we use to determine interval of convergence? Or ratio? Yeah, ratio test. Radius of convergence, ratio test. So I'm going to go ahead and just write ratio test. Now remember, the ratio test is really a test for absolute convergence. So if you have an alternator like we do, you don't even need to include it, okay? Because as long as it's just -1 to the n plus 1. If it had been like, let's look at this off to the side. If it had been -2 to the n plus 1, now you'd have to be a little bit careful because that does two things. It does alternate, but it also contributes to the growth. How can you separate the alternator from the magnitude generator? Yeah, you have to do some kind of factoring. -2 is the same as -1 times 2, right? And then because they're two separate factors, you can give each of them their own exponent. So you could do that and then this. Okay, so that's how you would separate. And sometimes that happens, like on a geometric series. But in this case, it's just -1. So we don't have to worry about that. So we'll take the n plus first term, which is x minus 5 to the n plus 1, all over n plus 1 times 2 to the n plus 1. And then instead of dividing by the nth term, or the absolute value of it, we'll multiply by its reciprocal, which is n times 2 to the n, all over x minus 5 to the n. And then from there, we start simplifying. And it should work out kind of nice. It's also kind of fun. Let's look at the x minus 5s first. We have one more factor of x minus 5 in the numerator, right? So all of them will divide out except the one in the top. So we take care of that. And then we'll look at the powers of 2. We have 2 to the n up there and 2 to the n plus 1. So we have one extra power of 2 where? In the bottom. And now we're left with an n and an n plus 1. Okay, so remember that we're still taking the limit as n goes to infinity, so anything that's not an n we treat as a constant. So really you could think of the top as being a linear function, n to the first, with a coefficient of x minus 5. And the bottom, if you distribute the 2, would be 2n plus 2. So the bottom is also n to the first with the coefficient, leading coefficient of 2. Yeah? It's still here. I just brought it straight down. It's right there. So I just did x minus 5 times the n. These 2's divided out. We're left with 1, 2 in the bottom. These x minus 5's are gone. We're just left with the n plus 1. So I just put the n's parts at the back. Okay, so really, again, it's n to the first over n to the first. and we're taking the limit as n goes to infinity, it should be leading coefficient over leading coefficient, right? Which is x minus 5 over 2. Okay, because you're treating x like a constant. So x minus 5, the entire quantity, is the coefficient of n. Now, notice we still have an x left. In the previous problem, when we took the limit, it went to 0 because there was no n in the top. Now we still have an x. So this is going to converge when it's what? Less than 1. So here's what we want to do. We want to find the values for which it converges. Now, if you still have an x left, here's your goal. This is what you want to try and get it to look like. You're going to want it to look like this. The absolute value of x minus your center less than the radius. If you can get it to look like that, you'll be staring at your radius. Well, all we have to do is multiply both sides by 2. We can take the 2 factor out of the absolute values because it's already positive. So if we simply multiply both sides by 2, we get less than what? Just 2, yeah. So this is our target. This is our goal. We got it. So what this means is the series will converge for all x values within 2 units, that's what less than means, of our center of 5. If you remember how linear absolute value inequalities worked, this is how it worked. You'd go to your center of 5, and then you'd go plus 2 this direction, and minus 2 that direction. So as long as you're within 2 units of 5 on either side, it's going to converge. Well, what's an upper bound then? What's 5 plus 2? 7, and 5 minus 2 is 3. So the radius of convergence is equal to 2. So sometimes you're just asked to find the radius of convergence, and that's going to be the value on either side of the center. Sometimes I might ask you to find the interval of convergence, and this one does. The interval of convergence is the domain of the series. They're one and the same. So here's how you would find the interval of convergence. Once you find the radius, you're going to take your center, just like we did, and say plus the radius for the upper bound, minus the radius for the lower bound. So that's going to span from 3 to 7. But here's the deal. It can either be from 3 to 7 with open or closed parentheses. When we say the radius is 2, we mean that it could be 2 exactly or just up to 2 but not including 2. In other words, we don't really know anything about the endpoints just by finding the radius. We can test the endpoints, and that's what you always have to do next. You're going to test the endpoints. This thing may converge at 3, may not converge at 3. It may converge at 7, may not converge at 7, but for sure it converges at everything between 3 and 7, for sure. All right, so how are we going to test the endpoints? Well, remember, these are x values, yes? We're finding essentially the domain, so those are x values. So let's test the endpoints by plugging those values back in way up here at the top into the original series, okay? So I'm going to make a little line right here, and we're going to say when x equals, let's do the lower bound first, when x equals 3. And all you got to do is plug your 3 in right there for x. And so we're going to have the series. It's going to be negative 1 to the n plus 1. 3 minus 5 is negative 2. All over n times 2 to the n. And by plugging in a specific value of x, now it's a series just like it was in 9.1. There's no x in it anymore. So let's go ahead and simplify. Negative 2 to the n and 2 to the n, do those divide out? Not quite. We have a negative 2 to the n. So what did I just tell you all we could do with that? Yeah, we could factor out a negative 1. So we could really call it negative 1 to the n times 2 to the n. We could split it up. So let me do that. That's negative 1 to the n times 2 to the n. And it's all over n times 2 to the n. These are kind of fun. They're like puzzles that just kind of come together. And now, what happens with your 2 to the n's? They divide out. And now we're left with negative 1 to the n plus 1 times negative 1 to the n. When the bases are the same, what do we do with the exponents? We add them. So that's going to be negative 1 to the n plus 1 plus n, which is 2n plus 1, all over n. Now, here's where you have to be careful. Is 2n plus 1 going to alternate the terms every other sign? If you're not sure, just try it out. Just try it out. Plug in a 1, and you're going to get what? A 3, right? Negative 1 to the third is a negative 1. Plug in a 2. 2 times 2 is 4. 4 plus 1 is 5. Negative 1 to the fifth is negative 1. I got 2 negatives in a row. Guess what? 2n plus 1 is always going to generate an odd number, which means it's always going to generate a negative number. Okay, so you got to be careful. Negative 1 to some power is not always an alternator. It's got to be like n plus 1, or n minus 1. So this is really the same as negative 1 to the n. That's the easiest way to tell if it alternates. Just plug in 2 consecutive numbers. Well, that's the same as negative 1 over n, which now we know does what? That diverges. That is straight up your divergent harmonic series, which is important because if this were in fact an alternator, it would converge by the alternating series test. So here's the deal. If it diverges when x is 3, then we are not going to be able to include 3 in the interval. It converges right up to 3, but not at 3. Now, how do we know if 7 is going to work? Same thing. So here we go. Second verse is the same song. You're going to get sigma, negative 1 to the n plus 1. And now, when you plug in a 7 for x, you get 7 minus 5 is 2. So you get 2 to the n, and it's all over n times 2 to the n. Now what happens with your 2 to the n's without any adjustment? They divide out. And we are left with now negative 1 to the n plus 1 over n, which is in fact now an alternating series. And so this one actually converges by the alternating series test. So if it converges at the right endpoint, what do you think about including it or not including it? We can include it, okay? So we would say then that this series has a radius of 2. It's a lot easier to find the radius. You don't have to test the endpoints. But if you want the interval, then you have to establish the upper and lower bound and then test the endpoints separately. We would then say that this series converges on the half-open interval from 3 up to 7 inclusive, which means that's also the domain of the series. In other words, here's a series that beautifully and perfectly represents some function, we don't know what function it is, exactly, perfectly, not an approximation, exactly, perfectly, everywhere from 3 to 7. Okay? And why is it perfectly and exactly and not an approximate? Because we're using how many terms? Infinitely many. So when we use infinitely many terms, the values of the series and the function it represents are the same everywhere on that interval. Okay? So interval of convergence, synonymous with domain of the power series. Kind of fun. It's a long, elaborate problem. Guess where these kind of show up? Free response. Yeah, and they kind of talk you through it. A radius of convergence is a pretty good multiple choice type question. They're a lot faster. All right, let's look at this guy here. Is it a power series, yes or no? Sure is. We've got an x. What's the center of this power series? The center. 0. Because if you were to rewrite that, it would be x to the n over 3 to the n. And because it's x minus 0 to the n, this one's centered at 0. Okay? You could use the ratio test here if you want, and it would work. But do you recognize this almost as some other type of series? Like if you plugged in a value of x, like let's say 3 or 2. If you plugged in a 2 for x, you'd get 2/3 to the n. That sure looks a lot like a what? Or 1. Plug in a 1 for x. That'd be 1/3 to the n. Doesn't that look a lot like a geometric series? It does. Okay? So if you did the ratio test, it would work. But sometimes you might recognize, oh, that's just a geometric series. And when does a geometric series converge? When the absolute value of the ratio, which is the base, which in this case is x over 3, when it's what? Less than 1. It kind of has the same thing as the ratio test. Well, in this case, our goal is to get it as x minus 0 less than the radius. So if I multiply both sides by 3, I get the absolute value of x, which is really minus 0, is less than 3. Guess what the radius of convergence is? 3. So this thing would converge if the center is at 0, plus 3, minus 3. Now, do we really need to test the endpoints here? Or do you know what the answer is? If this truly was geometric, if I let x equals 3, you could test it, right? Plug it in. 3 over 3 is 1. What happens to 1 to the n? It's always 1, so it diverges by the nth term test. So you can't include 3. What about negative 3? What's negative 3 over 3? Negative 1. What does negative 1 to the n do? Plus 1 minus 1, plus 1 minus 1. It alternates, so it also diverges by the nth term test. So the radius of convergence is 3, and what's the interval of convergence? If we can't include either endpoint. Yeah. As long as it's strictly between negative 3 and 3, you're going to have an exponential decay function. All right? So that's a quicker way to get to really the same result that the ratio test would give you. Let's see with the ratio test, because maybe you wouldn't recognize that as geometric series. I hope that you would. But if not, the ratio test always works. So let's see what that would look like. You would have the limit as n goes to infinity. And then you would have x over third to the n plus first power all over x over 3 to the nth power. And remember, it's a test for absolute convergence. So it would look like that. And now, since we have the whole thing to the n plus first power, all of them divide out except one of them in the numerator. So we just leave it like this. Now what happens to the n's? There are none. So remember, we're treating this as a constant. What's the limit of a constant? It's itself, right? It's a constant. So here would be the limit. And then you would say it's less than 1. So the ratio test gets you to the same thing that the geometric series test would. Exactly the same. Not every power series, though, is a geometric series. So you can't always use that. The ratio test will work every time, for the most part. So if you just want the one tool, that's fine. There's a lot to remember at this point in the year. Indeed. Okay. Let's look at this guy here. Power series, yes or no? Yep, sure is. It's got an X in it. It's also an alternating series. See it? Now, this then, with infinite limiting terms, represents for sure some function. But where does it represent it perfectly? I don't know. What's the center of this series? It's still 0 because it's not x minus 3 or x plus 3 or anything to the 2n plus 1 power. It's just x. So we know for sure it converges at 0, right? We know that one value. It always converges at the center. But are there any others? Well, let's do the ratio test. This one is not geometric. So the limit as n goes to infinity, absolute value. Do we need the alternator? Nope. Now here you got to be careful. It's going to be x to the. If you replace n with n plus 1, you got to distribute the 2, right? So that'll be 2n plus 2 plus 1, which is 2n plus 3, all over, same thing down here. Replace n with the quantity n plus 1, distribute, you get 2n plus 2 plus 1, which is 2n plus 3 factorial. And then instead of dividing by the nth term, we'll multiply by its reciprocal, 2n plus 1 factorial, or x to the 2n plus 1. And again, because it's an absolute test for convergence, we don't need the alternator. Now this one will simplify in a slightly different manner than we're used to. I like to build the shelf there. We have how many more x's in the top than the bottom? We have 2 more in the top now, right? Plus 3 versus plus 1. So if you just wanted to subtract 2n plus 3 minus 2n minus 1, we're left with x squared in the top. And then 2n plus 3 is bigger than 2s plus 1. So if we write it like this, 2n plus 3, the next one smaller would be 2n plus 2, right? And then the next one would be 2n plus 1, which then we could tie off with the factorial. So then the 2n plus 1 factorials would divide out. So we're left with 2 other factors there. And now, remember, we're treating x as a constant. N is our variable. So essentially we have a constant over a 4n squared if you expand out the leading terms. What's that going to go to? That goes to 0. And we know that this thing converges anytime that ratio is what? Less than 1. Do we have to find the values of x for which it's true? No. Just like with e to the x, this thing is always 0. So it doesn't matter now what x is. It could be 100. It could be negative 100. This thing is always going to be 0, which is always less than 1. So the radius is what? Infinity. And the interval of convergence is what? All real numbers, yeah. Or negative infinity to infinity if you technically want to write it as an interval. The domain of this power series, much like e to the x and sine of x and cosine of x, is all real numbers. The only bad thing is we don't know what the function it represents is, like sine or cosine or e. You could, if you want, you could generate probably 15, 20 terms of this and type them into your calculator in Y1 and hit graph and get a really good idea of what the graph of the function it represents looks like. But maybe then you wouldn't even recognize it. You wouldn't be able to find the equation. Okay, sweet. And then finally this guy here. Last one. Power series, right? We got an x. What's the center? 3. The center's 3. Good. So we know for sure that this guy converges at 3, right? For sure. Always. But are there more values? We shall see. Let's take the limit as n goes to infinity of the absolute value of the n plus first term is n plus 1 factorial times x minus 3 to the n plus first. Now, we don't have a quotient in our a sub n, so I'll just divide that one by what was given, n factorial x minus 3 to the nth. And now, like the Marines, we simplify, do or die. Something like that. Simplify, I think, is theirs. Yeah. But if you're like a math Marine, right? Simplify. N plus 1 over n factorial, which one's bigger? N plus 1. So I would write the top as n plus 1 times n factorial. And so the n factorials would divide out. So they're gone. And then my x minus 3s, I have more of them in the top or bottom. Which one? Top. How many more? 1. So I'm just left with x minus 3 in the top. So I really don't need this shelf. Go. So remember, x minus 3 is a constant, essentially, at this point. So what happens to n plus 1 as n goes to infinity? It goes to infinity. And what's infinity times a constant? Infinity. So this equals infinity. Remember, this only converges when it's less than 1. Is infinity less than 1? That's funny. It's not. So are there any values of x that's going to make infinity less than 1? No. So guess what the radius of convergence is? Very good. The radius of convergence would be 0. And now the interval, there is no interval convergence, right? We would just say that this one converges only at x equals what? And what was our c value? 3. Yeah. So there is really no interval. The domain is 1 point. That's not a very useful power function, right? It represents this function exactly everywhere at the center only. Okay, at that 1 point of the sig. And so the difference is between a polynomial and this is that, again, we're using infinitely many terms. A polynomial has no chance at representing a function everywhere, right? Because it's a finite number of terms. So it will always only be the same at the center. But these infinite series can wrap around a function beautifully on an interval. So this makes a good multiple choice question. It could say this series converges for what values? And of course, it could be all real numbers, no values of x, or just at x equals 3. So that's why you have to remember, even if the radius is 0, even if this is never true, the series will still converge at the center, still at that 1 point. All right, y'all got radius and interval of convergence down? It's kind of fun, right? It's not stuff you typically do every day. We'll now look at a very special family of power series for which you've practically already acquainted yourself, the Taylor-Maclaurin series. So really the only difference between the Taylor polynomials and Maclaurin polynomials in the series is instead of stopping at a certain term and using squiggles, we're going to go on forever and ever and ever, and we'll use equal signs. So this is still the most important part of a Taylor and Maclaurin series. It gives you the way to generate the coefficients and the variables, so you're going to need a differentiable function. All right, and just like before, if we centered at 0, the Taylor series is called the Maclaurin series. Okay, it says, notice we don't use an approximation sign, right? We use an equal sign now. Example 3, find a Taylor series for f of x equals e to the 5x centered at 2. Give the first 4 non-zero terms, and then here's what usually gets thrown in there, and the general term. Okay, so we might not get to finish this problem, but here's what I want to do. In the previous section, we wrote out the first 4 non-zero terms of the polynomials, and I said you know how to continue the patterns. It's kind of important to know the nth terms for those 3. So let's go ahead and do that. Sine of x now is equal to, not approximately, but it's equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus dot 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 plus, and now help me come up with the nth term. Well, the first thing I'm going to write is -1 to the nth power, or n plus 1. It could be either one, but I know that terms alternate. So I may come back and add a +1 there, but I know it's going to be either -1 to the n or n plus 1. Now it looks like it's going to be x to, what do we say about all the powers? They're what types of numbers? Odd. And how do we get odd numbers? We've seen it already today. 2n plus 1, or 2n minus 1. So 2n's are always going to be even numbers. 2n plus 1 or 2n minus 1 are always odd numbers. And now here's how we can make our adjustment. Remember, it doesn't really matter here what n we start at, but this sign and this power need to be the same. In other words, when I get a 1, I need it to be positive. When I get out a 3, I need it to be negative. So if I plugged in a 1 into the exponent here, 2 times 1 is 2 plus 1 is 3, I get x cubed. Ooh, do I want that? No. So you could do this. You could say, okay, what if I started at 0? What if I plugged in a 0 for n? That would give me x to the 0 plus 1 is what? X to the first. So that would work. If we start at 0 instead of 1, that'll give me this. Now what happens when I plug in a 0 for this n? Do I get a positive number? Yes, I do. So if I start at n equals 0, these two then will match up with each term. All right, so that's cool. And then in the bottom, it's pretty easy because if you notice the exponents match the denominator, so this will just be 2n plus 1 factorial. So you don't have to worry about the n you're starting with. You don't have to declare it, but you do have to make sure that whatever n you get to start with that gives you the first term matches in the sign. Now, of course, we could also condense it down to this, and we now know we can start at 0 and go to infinity of -1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. Okay, so the pattern for sine is one thing, knowing how to generate terms one after the other, but whenever we start modifying these series, they're going to ask you for the general term, and so you're going to want to modify the general term as you modify the individual terms, so you don't have to like reinvent the pattern. All right, we'll stop right there. We'll start tomorrow with doing the same thing for cosine, and we'll do the same thing for e to the x, all right? And then you're going to want to probably memorize the general term for each of those 3 as well as the pattern, okay? Practice, practice, practice. This worksheet is hugely important. Even though we're not going to be turning it in, make sure you give it your full effort.